Hello, um, welcome to the Best Full Paper session. My name is Claudio Silva from NYU, and I'll be the chair for this session. Before we start, I wanted to talk a little bit about the papers, the best paper selection process. So this was chaired by Professor Heike Leite. Heike really did the bulk of the work here. And we had another 6 members, Alex Ender, Michael Gleicher, John Conholm, Vijay Narajan, myself, and Penny Higgins. So the way this process worked was that we were given a set of 27 papers that were nominated by the area chairs and reviewed by the overall PC chairs. And we were tasked with selecting a set of best papers and a set of honorable mention papers. The way that this worked was that Heike set up a process where everyone had access to all the first round reviews, all the final versions of all the papers, and we all ranked the papers separately. And then we had a joint meeting, so where we tried to hit consensus. And it was actually fairly easy to hit consensus. There is really a set of wonderful papers this year for us to do. And in this session, we're going to see presentations by the 5 best paper awards that we selected. But I want to highlight that we also have 14 papers that receive honorable mention. These are wonderful papers, and I'm not going to read them all here, otherwise it would take a while. But I want to congratulate all the authors for doing this work, and I encourage people to read those papers and to watch their presentations later this week. So without, we are very short in time here. So without further ado, let's start with our best paper presentations. So our first paper is going to be Entanglements for Visualization, Changing Research Outcomes Through Feminist Theory. The paper will be presented by Derya Akbaba, right? And it's co-authored with Lauren Klein and Miriah Meyer. Derya, please go on.
Okay.
Do I need to stop sharing, I guess?
No, I think it's okay.
Okay.
All right, but maybe putting yourself on mute would help.
Sure.
Thank you. All right. Hi, everyone. My name is Derya Akbaba, and I'm a PhD student at Linköping University in Sweden. And I'm presenting on behalf of my lovely co-authors, Lauren Klein and Miriah Meyer. During this talk, I will cover entanglements for visualization, but entanglements is only one part of the story. If there's anything that you take away from this presentation, it's that we should care about how we come to know things in the world. To get to that point, I'm going to do something a little different with this talk. Instead of trying to squish 9 pages into the time slot, I'd like to share a different part of the paper, or rather, the backstory. Let's travel back to VIS in 2022. We're in Oklahoma City. Han had just presented our paper on data hunches when, in an unexpected surprise, Jessica Holman reached out via email to point out the similarities between data hunches and her team's investigations into Bayesian reasoning. The papers could not have more different titles. We were intrigued and decided to take a look. After reading both papers, we were shocked. The introductions to the 2 papers were completely interchangeable. In both papers, the authors called out that people are more than perceptual machines and that they bring their rich experiences to the interpretation of data. But visualization guidelines hardly acknowledge this. While it is one thing to read an introduction to another paper and feel like it could easily stand for your own, it is even more surprising that after the introductions, the papers completely diverge in methods, approaches, and results. How could two papers have the same motivation with interchangeable introductions, but result in radically different research? It turns out that different epistemologies lead to different research outcomes. When we started to write this paper, the one I'm supposed to be presenting to you about, we began using these two papers as our case study. We spent many hours with many multicolored highlighters, reading these papers together, trying to understand the ways in which research diverged from one another and why. As we read, we paid attention to how data, visualization, and people were both implicitly and explicitly defined across the works. We wanted to understand the differences that mattered. Reading the papers together revealed it's all about epistemology. And epistemology is the study of how we know what we know. We are constantly making epistemological assumptions in our work, and that changes everything. Epistemology draws our attention to some things and not others, scoping the research conclusions that we can draw, and shapes what we consider truth and how we validate it. And even though the papers followed very different epistemologies, when read together, their differences made our knowledge of the visualization problem richer and more robust. Different epistemologies also lead to epistemic differences, like how the authors defined the stuff that people were bringing to a visualization. In the Bayesian paper, this stuff was called implicit beliefs, whereas in the data hunches work, this stuff was called personal knowledge. The authors also outlined different visions for the role of visualization. In the Bayesian work, the authors demonstrate how Bayesian cognitive modeling can be used to evaluate how well visualization alternatives promote rational behavior. Whereas in the data hunches work, the authors envision that visualization can allow for the sharing of knowledge about the ways that data is imperfect, partial, and uncertain. These were some of the differences which ultimately led to radically different research results. Here's the thing, epistemology doesn't just change how we define stuff, it completely changes how we think about visualizations. Within a Bayesian epistemology, visualizations represent some version of the truth, and because of this, the author's work centers how to use visualization to promote rational behavior and interpretation of the visualization. Whereas within a feminist epistemology, which underlies the data hunches work, visualization represent just one perspective of reality. So the author's work centers how to use visualizations to support communication of multiple knowledges. Okay, so now we're back to VIS 2024. Nice to see you in the present. For the rest of my talk, I will continue to try to convince you that epistemology is important and that we need more of it. I will also cover the feminist entanglement theory for visualization that we outlined in our paper. And I want to be very clear that feminist theory is not just about ladies. Feminism is a socio-political movement working for equality across gender, sexual orientation, race, ability, and other marginalized identities. Whereas feminist theory is the study of the role of power and privilege in scholarly accounts of knowledge and truth. Feminist epistemology has a long history of looking at how power and privilege affect how we know things in the world. It rejects the idea that knowledge is disembodied and observer independent, and instead embraces the subjectivity of how knowledge comes to be, located in a specific time, person, and place. The specific feminist theory we draw on our paper is entanglement theory. And this theory was developed by theoretical physicist Karen Barad, outlined in their book, Meeting the Universe Halfway. In this book, they use unintuitive aspects of quantum mechanics to question more broadly how we come to know things in the world. In our paper, we translate Barad's theory into a visualization context. To explain entanglements for visualization, I will start with a simple model made up of data, visualization, and insights. And yes, let's not forget our researcher, because all knowledge comes from someone who is somewhere. When we apply entanglement theory for visualization, this simple model begins to get a little more complicated. Let's start with data. Data are static representations shaped by the standards and conventions and thinking at that moment, but the world is always in flux. If we look at census data as an example, census data are meant to represent a country's population. But people don't sit still. They move, they die, they give birth, and they cross borders. Census data is also shaped by many decisions and motivations. Who is counted as a resident or not, or when and for how long the counting happens. Data are never raw. They are shaped by history and social context and carry political power. Through entanglement theory, we can also unpack the many ways visualizations are entangled. For example, when we create new tools for biologists, the visualization is not only a reflection of our understanding of the problem at hand, but also entangled with the scientific interest of our collaborator, availability of new funding, and the tech stack we want to use. Entanglement theory also shows us that the visualization we call aesthetically pleasing are entangled with the history of how certain visualizations were valorized over others. And finally, we'll look at entangled insights. Entanglements draws our attention to how insights represent entangled stuff in the world and how they come to be. In other words, entangled insights are meaningful because of all the entanglements of data and visualizations, which includes all the stuff that they are entangled with. So how can we evaluate our tools if the tools themselves are entangled with a whole bunch of stuff? In the end, entanglement reveals that everything is connected. And when we try to diagram it out, it becomes this beautiful, inseparable mess where everything is connected to everything and everyone. The past determines our present as much as our future. So it looks like we've made a big ol' mess. Should we just fall on our heads and give up? Of course not. The strength of entanglements is that it shifts our research attention to different parts of a problem. It does not mean that we need to solve everything all at once. Instead, it is an opportunity to approach research in a different way. Entanglements for visualization directs our attention to different sets of questions, like what is our responsibility to understand and even account for the ways data are created in the world? How do standards for evaluating visualizations reflect certain value systems over others? And what would happen if visualizations exposed these types of entanglements? And other epistemologies bring forward other sets of questions to pay attention to. And luckily for us, it turns out that there are others in the community bringing in new epistemologies. We've begun to see researchers that are pulling from behavioral economics and statistics. Others are turning to the learning sciences, and others are entangling visualization with a feminist lens. Multiple epistemologies can provide an intellectual toolbox for visualization research. Every epistemology comes equipped with a different set of tools and methods, drawing attention to some things and away from others. To wrap up, in our paper, we call attention to how different epistemologies lead to different research outcomes. And in this paper, we present a new theory, entanglements for visualization. But this is just one of many possible epistemologies. And there's room for more to coexist and to strengthen the theoretical foundations of our field. So thank you to the reviewers and the Best Paper Award Committee for engaging with and finding value in our work. I'm graduating next fall and looking for a new position. Thank you all for listening.
Virtual applause to Derya here. Do we have questions? Maybe I start with a question on my own. I thought the paper was really fascinating, and I was trying to understand how it relates to this whole area of responsible AI, right? Because I think that it seems that many of these issues related to entanglement seem to be related to that. Have you considered how there's a literature in responsible AI and how it relates to your work?
Are you talking from a specifically visualization context or just a responsible AI context? So like the field of AI and machine learning.
I thought that it was somewhat that there was an opportunity for some of the framework that you're developing to also spill off to responsible AI, because there one of the things is not to take results on a vacuum, right? So you just take data and then, you have results that data, but then if the data that you put into the algorithm was biased or, so some of your case studies seem to remind me of kind of like the same flavor of work in responsible AI. So that's
Yeah,
why.
I understand your question. Thank you. Definitely. I mean, AI gets a lot of its power from the data that it uses, and entanglements as an epistemology shows us that data are never apolitical. And visualization can play a very strong and important role in maybe reminding the user or bringing these entanglements forward. And I think it's an exciting opportunity to explore in Viz research.
Cool. So let me take a question here. So there's a question: how does entanglement corresponds with intersectionality? I love learning about internationality in data feminism. A wonderful book by Ignacio and Klein.
By who? I didn't catch the last part.
Ignacio and Klein.
Yeah, so one of the authors is Lauren Klein, who's a co-author on this paper. And I would talk about intersectionality as, entanglements as an intersectional feminist epistemology. So for those in the room, intersectionality is a view on feminism that talks about how the ways that different marginalized identities experience bias in different ways. I won't go into more detail, but entanglements definitely speaks to intersectionality, and thank you for that question.
So there's another question here. Great talk and lovely presentation. What do you think are the next steps that we should all do to our research, or what are promising next steps?
That's a great question. So, admittedly, this project took 4 years, and we were working with Lauren the whole time. And it meant that Miriah and I really had to get out of our comfort zone and learn about other epistemologies that we weren't used to. So in the paper, we have some recommendations of what we suggest people can do. I'm not suggesting that everyone spend 4 years with a humanities domain expert, but I'm also not suggesting it. We learned so much, and now the way that I look at my own research is very different. Otherwise, I do see the value in starting to ask questions about things that we take for granted. So often we take data for granted that because it comes from our collaborators, it's not something that we can question, but maybe it is. Maybe this is something that we should start thinking about. Yeah, and sort of again in the paper we have a few provocations where we put forward what does it mean to research with and design with entangled data, entangled visualization, and entangled insights. So recommend reading the paper.
Thank you so much. Thank you for the thought-provoking paper. Congratulations to you and your co-authors. And we're going to move on now to, there are actually questions in Slido, but we're going to move on to the next presentation. Thank you so much.
Thank you.
So we now, the next paper, I think it has to switch over to oh yeah, it's right there. So the next paper presentation is going to be Aardvark, composite visualization of trees, time series, and images. Devin Lange is going to be presenting the paper, and his co-authors are Robert Judson-Torres, Thomas Zangle, and Alexander Leck. So Devin, please.
Great, thank you for the introduction. Let me just get the room set up going here. Just make sure the people in the room can watch as well, ideally. how did I do this? View. All right, thank you for your patience. One last thing here. If I do this. All right, the joys of virtual presentations. Great. So a little teaser for what I'll be talking about, but thanks again for the introduction. My name is Devin, I'm a PhD student. I was a PhD student. I just got my PhD a couple months ago here at the University of Utah, where I'm presenting live to a hybrid audience. I have started my postdoc at Harvard Medical School with Niels Galenborg in the High Dive Lab. With that, let's jump right into things here. Easy peasy. This research project is a collaboration with two labs at the University of Utah. And I would characterize the work that these two labs do as trying to understand cancer cell development. In other words, they want to know how cancer cells grow, divide, and spread throughout a body. Because if we can understand the mechanisms that drive these things, we have a shot at developing strategies that can prevent them. So you may be asking yourself, okay, Devin, this sounds great, but how do we actually do this? And the approach our collaborators take is they collect data on these cells as they're growing and dividing. So let me talk a little bit about the data that we are collecting. They start by collecting microscopic images of cells as they are growing over time. From these images, they can track these individual cells from frame to frame to end up with these individual cell tracks. In addition, they calculate derived attributes. These are things like the cell mass or size over time, resulting in multivariate time series data. And then ultimately, many of these cells will divide into two daughter cells. If we record this division, what we end up with is a tree of relationships or a cell lineage. So these are the three data modalities that we are working with: images, time series, and trees. And recall that my goal with this, the goal of our collaborators, is to understand the development of cancerous cells. So in our paper, we go into much more detail for all of the tasks that make up their interactions with the data. And we group these tasks into higher level categories: quality control, discovery, and communication. But for my talk today, I would like to focus a little bit more on the visualization tasks here. And there's three really important ones: spatial relationships, trends, and topological structure. So spatial relationships deal with which cells are close to each other versus far apart, things like this. Trends relate to how cells change over time. So a cell can grow linearly, exponentially, or maybe you want to identify some large spike in some attribute. And the topological structure really deals with this cell relationship. And you're looking at things like, here you may see that the top branch is dividing a lot, but the bottom branch is not. So some asymmetry in the topology. But okay, actually I lied. There aren't three important ones. There's one very, very important one, which is the synthesis of all three of these. In other words, synthesizing all three data modalities. Our collaborators aren't doing just one of these for a long session. They're constantly doing all of them and trying to understand all pieces together. And this is really the core challenge that we are trying to address with our visualization work. But this is a little bit abstract, so I would like to give a couple of examples here. If we think about the time series data, we can see as one cell grows, divides into two cells, grows, and then divide into 4 cells. And a visualization like this can be very informative. You can learn a lot from it. But what if the data looks like this? Think about this for a second. When you see this, you may ask a question like, is this cell actually growing abnormally large? Or is this an error in the data? And the only way to answer this question is to find the corresponding image in your imaging data. Let me give a second example. Let's say you find an interesting pattern, like this divergence of cell growth. You may ask a question like, okay, are these fast-growing cells here dividing into these fast-growing offspring? Again, the only way you can possibly answer this question is by looking at this other data modality and relating the elements together. And we find that our collaborators are sort of constantly doing this relation across data modalities. So our goal was to create composite visualizations that stitch these elements together into a single view. Of course, these composite visualizations are not new. I'd like to specifically call it Javed and Elmquist for their nice design space on this topic. And in our research, we use the same framework, and you'll be seeing in particular a lot of these superimposed views and nested views. So let me jump into our first example. In this composite visualization, we begin by selecting the tree as our primary data type, which serves as our host visualization. Shown here is this node link diagram. We can then embed our secondary data types as Klein visualizations by nesting them, for instance, like the time series data, and superimposing images either automatically or on demand as the user interacts. Let's shift gears and look at this view within the actual software we developed called Aardvark. We'll talk about all three of these composite visualization views, but I'd like to begin with this tree first view. So let me open this up to full view. In this visualization, the multivariate time series data is shown with these horizon charts. The images are shown automatically at key points, like where cells divide, or where there are these large changes in the attributes. Now, as I interact with the system, additional images can be drawn as space allows. And as I compress it, those images will be removed. But at any point, I can select along this horizon chart to see that individual cell, or I can select the existing thumbnails to see the previous and next frame. And in this case, we actually see something quite interesting here. In reality, this particular cell that is outlined has divided right here into two daughter cells. But this algorithm has made a mistake and is identifying this one daughter cell as the same as the parent cell. Let's move on to our second visualization. Here we use time series data as our primary data type, which we can then embed some of the tree relationships on demand, as well as the images on demand. I think this will make more sense in Aardvark. So let me open up this view. And here we can see as I mouse over the line, this individual cell is shown at that moment in time. And when I select it, the cell relationships are shown. So let me walk you through this construction. This selected line that I've just drawn is showing the mass for one cell over its lifetime. So the cell is born with a small mass, it grows, 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 and then it divides with a larger mass. So moving backwards in time, we have a connection, a dashed line drawing the relationship to the parent cell. And then moving forwards in time, we have a dashed line connecting it to its two daughter cells. These daughter cells are given distinct colors, green and purple, to help distinguish them, but also to help draw connections to the next generation. So the green cell has green offspring, and the purple cell has purple offspring. So now that we've built this, let's think for a second about what we can see here. And in this case, we actually do see some of that divergence in growth. These green and purple cells all came from that one founder cell that we selected. But we see that the green cell has grown larger here and divided sooner than the purple cell. Moving on to our third composite visualization. Here we have images as our primary data type, which we display as an image and then can embed the cell movements superimposed on top of them. The relationships can be shown for the cells on screen. So we show green marks for the current cells. And then for cells that are siblings, we draw a line connecting them with a circle indicating their parent. In this case, the two parents are also siblings. So we draw a line to connect them and then draw another mark for their parent or the cells on screen's grandparent. So in Aardvark, this experiment isolated one cell that divided into two, then four, then eight. And then these cells ultimately become so populated that they actually get pushed over and begin to overlap, which we can identify here. So taking a step backwards, these are all the composite visualizations we just talked about. I like them. I think they are quite nice at the task that they are doing. But the task that they're doing is for live cell microscopy imaging with lineage tracing. So raise your hand if you're currently working on a visualization project that does that. I don't see anyone, but my guess is that not many people are raising their hands for this. So my point is, what are the larger takeaways that maybe you could learn from this work? And this really comes down to this design of composite visualizations that applies beyond this use case. So thinking about the challenge, there's many data modalities, and each of these can be drawn with different encodings, different visualizations. And then on top of that, you have many different ways that you can compose these visualizations together to create your final combined view. And really the point I'm trying to make here is that this design space can feel quite large and intimidating. So I'll leave you with one very concrete piece of advice, which is to start by thinking about your tasks, think about the most important task, and select the data modality that answers that task, and choose a visualization or encoding that best solves that particular task. This choice will serve as an anchor in this sea of design choices. And in our experience, this will also drastically cut down on the number of other possible choices you need to explore. So with that, I'd like to shift gears and take 20 seconds to talk all about me. My name is Devin Lange. Feel free to reach out on email, follow me on social media, hire me. Okay, I just started a postdoc with Neil, so I don't need a job right now, but I am pursuing a career in academia and visualization. So please keep me in mind in the future. We are having hybrid coffee events here, so have a coffee with me and my friends at Utah, and check out my poster. So with that, I'd like to thank the audience. I'd like to thank the reviewers and the award committee, and also thank the visualization organizers for organizing 3 conferences this year.
Thank you, Devin. Thank you very much for the wonderful talk and for your great paper. I will start with a question. So I'm interested to understand what your data layer looks like for this, because it seems to me that you have you have like potentially like a large collection of images that then you have to compute a lot of like derived data, right? That is the stuff that you show in the time series. So how do you store it all? Like how I mean I wonder how how complex your data layer for this is.
Yeah, thank you for the question. How is the data structured? I finally get to use this slide in my appendix for the first time, so thank you for asking this question. But you're exactly right? We have these stacks of images, and there are, maybe there's multiple imaging locations for one experiment. I didn't get into this in detail, but you can get a plate and image 1,000 locations in one single experiment. And you want to like conceptually think about this as an experiment. So we have these experiment JSON files with metadata that point to these imaging locations. Imaging locations have these stacks of images. We're now using these OME TIFFs, so open microscopy environment TIFFs, or more standard and used. And then on top of this, we have the segmentations for the cells. For us, we were using these GeoJSON files. Turns out drawing borders of regions in geography is also good for drawing borders of cells. And then we essentially have tabular data for these metadata, the time series data. And now we're actively developing this project. We have a small team of developers, and yeah, actually we're using some binary tabular formats for it now. But this is the overall structure. And in terms of technical architecture, there's more or less a static file server that we query for the pieces that we need on demand. So yeah, we can talk more about this, but maybe let's move on to one other question.
Hey, thank you, Devin. Thank you. That helps me. There's a couple of questions here. So one is, did you try your tool with domain experts, and what was the feedback?
Yeah, the co-authors of this paper are the domain experts. So there are these 2 labs here who are doing experiments like this, and we've actually worked closely with them for now 4 or 5 years, we'll say. And essentially throughout the process, it's not like we developed and then tested at the very end, but throughout the process, we collected feedback, iterated, developed things. We ran these CVO studies, and yeah, that's kind of the process that we use for getting feedback on the tool.
Okay, so there's one more question here. Have you explored other types of compositions such as calendar, map plus bar chart?
So did we consider other design choices? Yes, I think, the tree first view in particular required probably the most iteration. And the first things we tried did not work at all. Which I wish I had an image show. Maybe if the person is curious, that we can talk afterwards. But instead of composing the images on top of the line chart, we tried embedding them within the line. And yeah, sometimes it's hard to explain why things don't work, but you just try it. You look at it for 10 seconds and it's like, this doesn't work.
Okay, so Devin, thank you so much for a wonderful presentation and for a great piece of work here. We're going to move on to the next presentation now. So let's see here when we move. So the next paper is VisEval, a benchmark for data visualization in the area of large language models. It will be presented by Chen. And they have co-authors Yuge, Jiahang, Han, and Yuqing. So Chen, please, start.
Hi, let me share my screen. Can you see my screen?
I'm still waiting, but I think it's probably coming. Let's see.
Yep.
It's okay.
Yes, it's there. Thank you.
Okay. Hello, everyone. I'm Chen from Microsoft Research. It's an honor to be here to present our latest work, VisEval, a benchmark for data visualization in the area of large language models. I'll be sharing this work on behalf of my colleagues, Yuge Zhang, Jiahang Xu, Klein, and Yuqing. Let's brief revised NL2Vs. This approach translates natural language queries into visualizations, making visualization more accessible for everyone. Automating NL2Vs has been a long-standing goal. The exciting news is that recent advancements in LLMs are unlocking new potential for this task. However, it remains unclear, are the visualization generated by LLMs reliable? Do LLMs follow best practice in visualization? Let's see some example. When generating visualization with LLMs, the usual process involves assembling a query and the data tables into a prompt. Then the LLM generated code using an established visualization library. And this code is run in an sandbox environment to produce the final chart. In this case, we ask LLMs to visualize the shape data set using a static bar chart, but all four models faced issues. Some produced code that failed to execute, others mismapped the data and used wrong legend, and some failed to sort or place elements outside the canvas. We can categorize these issues into 3 dimensions: validate, legality, and readability. Specifically, invalidate codes resulting in rendering fails. Illegal charts don't meet user requirements, and the charts with low readability make understanding difficult. These shortcomings highlights the urgent need for systematical evaluation, but current NL2VIS evaluation methods fell short. We reviewed existing visualization datasets and found several limitations. Some lack text queries or orange data, others lack ground truths, and some focus on narrow domain and lack scalability. When it comes to evaluation methods, there are three main approaches. First, human evaluation, the gold standard, but it's time-consuming and resource-heavy. Second, rule-based methods check if AX and YX data match the ground truth. However, they can be too strict if the query doesn't specify data mapping. Judging a rank to color mapping as incorrect just because the ground truth uses sex to color mapping may be unfair. Sometimes they are too lenient, missing error like incorrect legends. Additionally, it only focuses on correctness, ignoring readability. Lastly, LMS are now being used to assess generated code, but their reliability hasn't been fully tested yet. To address these challenges, we introduced VisEval. It features a high-quality large-scale dataset and an automatic NL2VIS evaluation framework that covers multiple dimensions, ensuring more comprehensive and trustworthy assessments. We built a high-quality dataset by focusing on unambiguous, rationale, and non-duplicate queries with accurate ground truths. To ensure robustness, we covered diverse domains and chart types, excluding overly simple queries. We use a large-scale NV-bench dataset as a base. To meet these two goals, we select high-quality queries with the help of LMS and human experts, balancing quality and reducing ground truth and reducing human workload. To achieve this goal, we annotate all accessible ground truths for each query with meta-information. Finally, we rebalance the dataset. As a result, we have a dataset with 7 chart types and over 1,000 visualizations. Next, we developed an evaluation framework to detect any issues we previously introduced, automatically assessing the generated code for validate, legality, and readability. To ensure a reliable result, human experts carefully review both the dataset and the framework. We also ran test case and perform quantitative evaluation to measure its effectiveness. Now, let me briefly introduce the framework. The first module executes the generated code and checks if it produces visualization, ensuring validity. Once the code passes the validity check, the legality checker deconstructs information like chart type and data from the visualization to assess their legality using the annotate meta-information. Finally, assessing the readability is the most challenging part, as it requires considering many factors like layout, scale, and color. To overcome these challenges, we leverage the power of GPT-4 vision and break down the readability assessment into smaller, manageable sub-questions, specifically layout checks and scale and text checks. Together, this contributes to a comprehensive readability evaluation. Our quantitative experiments show that the readability evaluator aligns well with human performance. Building on VisEval, we conduct several evaluations. Overall, we assessed first state of art LMS for generating visualizations using 2 visualization libraries. We also explored the difference between various prompt design, particularly focusing on table formats. Finally, we analyzed the impact of table disruption. Now, let's explore this evaluation in more detail. First, VisEval demonstrate its capability to effectiveness definition between different models. Our star performance GPT-4 Vision achieved a high quality score of 2.9 when generating visualization using Matplotlib, with optimal score being 5. While impressive, there's still room for improvement. When using Zangle, which is built on Matplotlib and offers a high-level interface, the code is always simpler than that of Matplotlib. However, the result for the LMS was surprising. None of the models scored higher. This suggests that there is less pre-trained data available for Zangle compared to Matplotlib. As we explore performance across various chart types and task hardness, a clear trend emerged. More complex visualization requires greater model capability. For instance, charts requiring 3 visual channels consistently receive low quality score compared to simple charts needing only 2 channels. Through deep analysis, we found that LMS tends to make errors at various stages of generation, such as code writing, data transformation, visualization transformation, and sorting. Beyond accuracy, we also discovered that LMS frequently face significant readability issues, an aspect that has often been overlooked. Next, we evaluate the performance of 3 maths with different prompt design using GPT 3.5 model, including previous work like LIDA, Chart2VIS, as well as our maths common for VIS. The result, well, it turns out how you design the prompt can have quite a few surprising impact on the model performance. Curious about this variation, we conduct more experiments. One thing that jumped out at us was that these 3 approaches use different table formats. Do different table formats affect model performance? To figure out, we keep everything common for these the same except the table format. The result showing that different LMS indeed have distinct preference. This reveals an important insight. We might need to design different prompts for different models. Finally, we test what happens when extra unused tables are added while generating visualization. By randomly including 2 unrelated tables, we saw a consistent drop in LM performance. This evaluation indicates there is room for improvement, and we identified several potential areas for development. First, LMS sometimes struggle with specific visualization libraries or complex visualizations. So integrating external specialized knowledge could help, such as fine-tuning the model with additional API document or successful visualization examples to enhance its understanding of visualization techniques. Next, since LMS often make errors at various stages of generation, decomposing the task into subtasks could address these issues step by step. For example, LMS often face readability challenges. Code alone may not address these issues, which if we generated visualization iteratively, guided by feedback from a readability evaluator. We could also add a table selection module to improve data understanding and ensure only the appropriate tables are used for the visualization. Finally, prompt design plays a huge role in LM performance. Even small tricks like changing the data format could have a big impact. To stay ahead in this fast-moving field, we should leverage automatic prompt optimization techniques to unlock the full potential of LMS. In conclusion, we introduced VisEval, a benchmark designed for visualization in the area of large language models. VisEval is not available online. You can access it by scanning this code. And additionally, more related work from our group is listed here, focusing on data science with AOMS. Thank you all for your attention. Before I finish, I would like to take a moment to express my deep gratitude to the conference committee for recognizing my work with the Best Paper Award. It's truly an honor, and I couldn't have achieved this without the support and cooperation of my colleagues. Thank you.
Thank you, Nan. So there are so many questions that I will ask one of the questions from the slide versus the questions that I was thinking. So it says here, given the rapid development of LLMs, do you think VisEval can evaluate more advanced models in this generation in the future, for instance, GPT-o1?
Yes, I think VisEval can evaluate emerging models because VisEval is a generalized framework not designed for a specific model or mass. So it is able to evaluate the new coming models, and we have open sourced our code and provide documents to illustrate how to configure our framework to adapt to new models or mass. So if you are interested, you can scan the code to access our report for specific examples.
Okay, thank you. Another quick question here. How difficult it is to extend this to work with like visualization libraries like D3 and Vega Lite?
Yes, I think it wouldn't be too difficult because our evaluation work is designed module. Our framework is module design. So if you want to expand our framework to other libraries, you can just change some part of our framework to a new library.
Okay, so thank you so much again. Congratulations on your paper. We are going to move on now to the next paper. Thank you.
Thank you very much.
Okay, so our next presentation, our next paper, let's see if it needs to get updated so that I'm checking when the screen updates. Okay, so our next paper is going to be VADIS, a visual analytics pipeline for dynamic document representation and information syncing. This is by Hu Chu, Yamei Tu, Po-Yin, and Han-Wei Chen. And I believe Hu Chu is going to be presenting the paper. Please go ahead.
Okay, let me share my screen. Okay, I think you guys can see my screen. Okay, thanks Claudio for the nice introduction. And hello everyone. I'm Rachel from the Ohio State University. It's a great honor to present our work, VADIS, a visual analytical pipeline for dynamic document representation and information seeking. This work is a collaborative effort with my co-authors Yamei Tu, Dr. Po-Yin, and also my advisor, Professor Han-Wei Shen. So our work addresses information seeking from large corpora, focusing on two main tasks. First, given a large group of documents, how to organize and display them in a way that highlights meaningful topic clusters, such that user can easily explore the semantic areas. Second, when users have specific research question in mind, we strive to identify and present the most relevant articles clearly and efficiently. So currently, the dominant approach to achieving the first task is by leveraging transformer-based models like BERT or GPT series of models. These models convert text into tokens, which are then processed through several attention layers. Each token embedding is then updated based on its attention to other tokens, capturing the contextual relationships. The model also reserves the special CLS token that aggregate information from all other tokens to form the final document embedding. This embedding represents the semantics of the article, and it can be visualized using techniques like t-SNE or UMAP for semantic clustering. So, however, we have identified a key issue within this approach. The document map produced often show with inconsistent grouping patterns. So, for example, some articles may be grouped together because they focus on a similar population, while others are grouped together because they study similar treatments. While this inconsistency arises because certain dominant features in the embeddings drive the grouping, leading to these mixed results. So ideally, we want a document map that can adapt to users' dynamic interest. For instance, if a clinician is interested in the population studied for each paper in the corpus, we will want the map to group articles based on different populations, such as children or teenagers. While conversely, if the focus shifts to the treatments, the article should be grouped accordingly. But soon, we found that when taking users' interest into account, another severe issue pops up, which is that given a specific interest in a large corpus with like 7,000 of articles, only a small subset of articles tend to be highly relevant. We conducted a preliminary study focusing on the side effect of a drug called MPH or methylphenidate for treating children with ADHD. We analyzed around 7,000 articles, and we draw here with x-axis represent the sorted document index and the y-axis showing the relevant score. You can see that only a small number of articles hold substantial relevance to the query, while the majority actually have much lower relevance. This actually creates a big challenge when we want to visualize these documents using a traditional scatter plot-based document map. Because if we rely on geospatial coordinates to indicate similarity and grouping, we are pretty much left with options like opacity or size to represent the relevant scores, which we consider are far from ideal. So to address these challenges, we start by exploring how to generate dynamic document representation based on users' dynamic interest. The idea is that when users have different interest, different portion of the original document content should receive higher attention score during the embedding generation, since the attention directly contributes to the resulting embedding. So we approach this problem by thinking about directly using users' query to guide the attention allocation from a series of document tokens. So the information here comes from two separate encoders, the query encoders, which process the user's query and use the final CLS embedding, and the document encoder, which process the document contents and generate text tokens for every single or every individual text tokens. And finally, those information are merged together, go into what we call as a PAM layer or prompt-based attention layer and generate this dynamic document representation. So during the training, we use the sum of a raw attention score before doing softmax, and basically this attention score derives how the query CLS token attends to the document tokens, and we use that as an indicator for the relevance of the query and the documents. And we then apply the contrastive learning to ensure that the model gives a higher attention to the relevant tokens in the pertinent articles. So one thing to notice that is we don't directly supervise the model to attend to the specific answer tokens. Instead, we let the model to figure out which tokens are relevant in each document such that they can retrieve the most relevant article. So the model here produced two key outputs. First, it generates an attention score for the entire document, which we treated as a relevant score for the article in relation to the query. Second, it produced a document embedding that is weighted by the softmax attention score. So with these two information, our next challenge is how to visualize them. So remember that we have the study of a relevance distribution, and it turns out that we found that this distribution can be naturally mapped to a circle layout. So the rationale is that the center of the circle being naturally smaller, it highlights the limited number of highly relevant documents. And as we're moving forward, the expanding peripheral zones can accommodate the increasing volume of less relevant ones. Therefore, we adopt the circle layout where the center of the map is conceptualized as the query's focus point, and the distance between each document dot to the center reflect its relevance. Additionally, our domain expert during the discussion and preliminary study expressed a preference for a grid layout over a continuous space to avoid problem like overcrowding. So therefore, our problem becomes optimizing the placement of documents in this grid layout, given that the relevance score and the embedding of each document. So our goal is to ensure that the documents closer to the center are indeed more relevant, while also grouping similar documents together. So the last function here, we use balance these two factors by introducing a weights for similarity omega s and also weights for relevance omega r. So these weights allow us to control the trade-off between keeping relevant documents near the center and also maintain a cluster of similar articles. Since this is a discrete optimization problem, gradient-based methods are not directly applicable here to determine the best allocation. Instead, we found that this problem is well suited to the competitive learning approach used in self-organizing map, SOM, which can be thought of as a discrete counterpart of the gradient-based methods. So to give a better intuition of the projection, let's see some simple results with the minister data set, digits from 0 to 9. So our setup here is that lower numbers, we give them higher relevance, so they should appear closer to the center when the relevance is prioritized. So let's first do some sanity checks. So in the first layout on the left side, we set the relevance weights to be 1 and the similarity weights to be 0. So the result projection highlight relevant digits like 0 at the center, with others spread out by the relevance from 1 to 9. Conversely, when we set the similarity weights to be 1, we see the grouping are done purely by verosimilarity without regard to the relevance. While in the middle two layouts, we balance the relevance and the similarity. So here, we take both factors into account and leading to a more integrated grouping. So this flexibility allows us to adjust the layout based on the importance of relevance versus similarity for each specific use cases. So now we have introduced our dynamic document representation model and the circle layout. Let's see how they come together in our Vero interface. So here in our interface, user can input multiple queries, adjust their weights, and we'll generate a customized circle layout. And in this interface also allows intuitive exploration of each individual document, with attention visualizations highlight the attention distribution among tokens. Well, as we began testing this interface, we noticed that a potential challenge. That is, if the user wants to examine the attention distribution for each document across the corpus, they pretty much need to hover over every single articles. This process can quickly become intensive and time-consuming. So therefore, a key challenge emerged. Can we provide a global overview of the attention distribution? So this will help users, especially clinicians, immediately understand where attention is concentrated on across the corpus, especially when they have a specific interest. So to address this need for a global view of attention, we draw inspiration from the topic modeling techniques, particularly non-negative matrix factorization, MMF. So in topic modeling, MMF decomposes a word frequency matrix into a topic and also a word distribution matrix. We apply this concept here, but instead of using word frequency, we use attention score. Since attention scores are dynamically assigned and reflect the importance, they provide a more accurate and flexible indicator than the static word frequencies. So by decomposing our corpus attention matrix, we got an attention topic matrix, which links the documents to attention topic, and also a topic token distribution matrix, which represent like how topics are distributed across different tokens. So this final matrix serves as our corpus level attention and allowing us to understand how attention is allocated across different topics throughout the corpus. So in our system, we just use a simple bar chart plot for display the corpus attention. As a result showing here on the right side, this is a sample one when user input a query like a population studied, and then attention just focusing on this 6 or 7 different topics. And we can see we have several dedicated topics focusing on tokens like population like teenagers or boys or children. So finally, in our evaluation, we focus on 3 key aspects: the effectiveness of our dynamic document representation model, the effectiveness of our projection, and also the usability of the entire system in the real-world tasks. Due to the time constraint, I will skip the third part, which is covered in our case study section in the paper. So first, to assess the model's effectiveness, we focus on two key metrics to assess. So I will give a high-level intuition here without diving too many details due to the time constraint. So first, retrieval accuracy measures how well the model can retrieve the most relevant documents from a corpus based on the user's query. This is how the model is trained. Essentially, we're testing if the model can accurately identify the correct document context compared to traditional models like BM25. The second measure is what we call as a relevance attention ratio. It's essentially evaluate how much attention is focused on the most relevant part of a document, the answer tokens. We consider that the higher of this ratio, the better the document representation is concentrated on the correct information. So for the projection, we evaluate its ability to group in similar articles and align the relevance perspectives. So using the silhouette score, which assesses the grouping accuracy, or method performed comparable to t-SNE, but you need to choose the similarity weights to be 1, with the score close to 0.33. We also introduced a relevance profile comparison matrix, which measures how well the layout relevance distribution align with the true data relevance. So with that, we come to the conclusion of our presentation. So in summary, we introduced a dynamic document representation method, and we realized it using relevance preserving mapping, which balanced both the relevance and similarity. Together, this approach formed the foundation of our interactive system designed to solve some real-world tasks for information seeking. Thank you all so much for your time. I would also like to give a heartfelt thanks to the wonderful VIS community and the Best Paper Committee for this amazing recognition. Thank you so much.
Thank you, Rui. So there's a few questions here. One of them is, why not use linear ranking with decreasing relevance with a cutoff point?
So yeah, that's a great question. So one thing we noticed that is if we just using linear ranking, that's pretty much like how we do in like a Google search, or if you search a keyword that basically pops up a bunch of similar articles. But what we actually noticed that within those highly relevant articles, there could be also some similarity. So if you just rank linearly by the relevance, well, if you're taking like consideration like clinician have a huge corpus like 7,000 articles, if you just simply list all of them based on the relevancy, they could not, this domain expert, they cannot see like there can be potentially some semantic clusters within these highly relevant papers. So that's why we want to give them an overview showing both the relevance and also the similarity grouping.
Okay, so one more quick question. What about the scalability of your technique? How scalable it is?
Oh, so yeah, that's also a good question. So for our test cases, because we are focusing on relatively short document, so specifically in our test, we only use the abstract of each articles. So when we extend this model, for example, to some long context using like if you're using llama as the backend instead of what we used BERT, there can be some scalability issue. But we actually come up with a solution because for the embedding generation, you only need to calculate the token embedding of the document once, and during the inference, you actually can just calculate the COS of different query, and then you just run the final attention layer to generate dynamic embedding. So
Okay.
yeah, we are also trying to we are doing our best to trying to improve this to the larger models. Yeah,
Okay.
hopefully we can get some good result. Thank you so much.
Sounds great. So thank you so much. Congratulations again on your paper. A great presentation.
Thank
So
you.
we're gonna go to our final paper now, our final best paper presentation. And let's wait until it shows up on the. This is a rapid and precise topological comparison with merged tree neural networks. Okay, it's by Yuqing, Brittany, Terese, Fasy, Carola Wang, and Brian Suma, and the presentation will be done by Chen. So take it from here.
Can everyone see my screen?
Yes.
Okay, great. Hi, everyone. My name is Devin, a PhD candidate at Klein University. As you know, this year's VIS conference has been impacted by two significant hurricanes. This actually highlights the critical need for rapid and precise data analysis and visualization in such situations. Today, I'm honored to share our work on rapid and precise topological comparison using merge-tree neural networks, or MTNN. Predicting a path of hurricane isn't just about forecasting. It's about processing massive, complex datasets in real time. We handle high-resolution simulations and capture detailed sensor measurements every second. The weather research and forecasting model generates gigabytes of data every second, checking how storm systems evolve, merge, and split. So analyzing this massive and complex data requires scalable tools that can handle both the data's global structure and local features. One such powerful tool is merge trees. A key concept in topological data analysis, TDA, is widely used to analyze the shape of data, focusing on its structure rather than individual points. So merge trees distill complex data like hurricane wind speeds into a concise and stable topological structure. Recent studies have shown their effectiveness in handling complex datasets, making analysis and interpretation easier. To demonstrate how merge trees work, I will start with a simplified example. In this example, we simplify the 2D scale field into a 1D scale field, where each point represents a function number such as temperature or wind speed. Now we have the 1D scale field. We identify critical points in the scale field such as maxima and minima. These points and their represent topological features define the structure of the scale function. By recognizing them, merge trees are applied to understand the function's behavior. Merge trees construction is grounded in TDA, a well-defined mathematical framework. Let's briefly go through how we construct a merge tree using sublevel set filtration. Imagine we are sweeping through a function like scale function from bottom to top, like flooding a landscape with water. We start at the lowest point or global minima, point A, with a function number of 1. This creates one connected component, node A, in the merge tree with a birth time of 1. As we continue to raise the water level to elevation 6, a new connected component node B appears with birth time 6. At elevation 8, node C is born. When we reach elevation 10, something interesting happens. Node A and C merge with node D in a merge event illustrated by this green region. Here, node C is dead because it's a younger node, so its death time is 10. Keep going to elevation 11, we have a new node E and 2 merge events. Node B and group of nodes A, C, and D are merged into E. Finally, this combined connected component continues up to our global maximum, node F, at elevation 50. So this shows how connected components are born and die in merge trees, capturing the essential structure of the data. In our merge tree, each node has 2 important features. Function number, this is a number of the scale function at that point. And persistence, which measures how long the connected component exists. For example, node A was born at 1 and died at 15, so its persistence is 14. Similarly, node C was born at 8 and died at 10, so its persistence is 2. By capturing these features, merge trees show where connected components appear and how they evolve, helping us understand the data's structure. Even if 2 functions have the same critical points, but connected differently, like this example, merge trees show how these differences effectively describe the data's underlying shape. And merges not only help analyze hurricane data, but are also applied across many fields like climate modeling, material science, medical imaging, and more. However, comparing merge is computationally challenging. It's an NP-hard problem for theoretical distances. Practical algorithms exist, but their complexities are bounded by the number of nodes. So you can imagine as the number of critical points increases, the computational complexity can grow exponentially, making comparison impractical for large data sets. For example, calculating the distance between two merges often requires matching nodes one by one, like eddy distance, considering like both the eddy cost and the differences in persistence, a time-consuming process for large trees. To address this, we transform the complex task of merge comparison into a learning problem, a smart integration of machine learning with merges. Our approach includes redefining merge comparison into a learning task. We designed a specialized graph neural network, GNN, for merges, but we go beyond GNN. By integrating TDA using topological attention, we capture the essential persistence information that's unique to merges. This leads us to MTN, the first machine learning model for merge similarity. Let me briefly explain how GNN works in our context. Given a graph like this, each node has a feature vector as node embedding. GNN updates this like node embedding by aggregating information from neighboring nodes through a process called message passing. Then we combine these update node embeddings into a graph embedding representing the entire graph. But our approach goes beyond just GNN. Standard GNN may not capture the function numbers in merges as well as the original data. As this example shows, different scale functions have identical graph representations. To address this, we assign node features based on their function numbers, making each node unique. Okay, now we include the function number in nodes. But how about the persistence, which captures the data's underlying shape and features? And it's an essential property in merges. To accurately compare merges, we need to include persistence in our model. To do so, we introduce what's called a persistence-weighted adjacency matrix. This matrix has nodes as rows and columns. So here, 0 indicates no connection. Red entries include persistence pairs, even if the nodes are like not directly connected in the merge. For example, A is born at 1 and death at 15, so its persistence 40 is included as a red entry. In standard GNN, we combine like all node embeddings like equally in aggregation. However, nodes with like higher persistence represent more significant features. We calculate attention weights based on this matrix, emphasizing important nodes when creating the overall or like tree embedding. Here is how we reweight the original node embedding. We first compute the total edge weights to capture each node's global importance, and normalize these weights to create attention scores in the global context. Then we reweight each original node embedding using its global context. This made our model focus on the most important parts of the merges, aligning with TDA principles. We train our model using pairs of merges and their known distances, allowing it to run the similarity scores. After training, comparing merges becomes simple. Input any pair into MTN, and it outputs a similarity score almost instantly, bypassing intensive like node matching. Okay, now let's see how MTN performs in practice. We evaluated MTN on 5 datasets, 1 synthetic and 4 real world. Here is the runtime for 1 practical merge distance or MT distance, plotted on a log scale due to the wide range of numbers. MTN dramatically outperforms MT distance and achieves over a 100 times speed up. In fact, even when plotted on a log scale, MTN's runtimes are so minimal. They are barely visible for these 3 datasets, as it reduces computation to like the order of milliseconds. Along the speed, MTN maintains high accuracy. The extremely low MSE shows reliable results. To evaluate MTN's performance, we also compare the similarity in MDS space. The top plot shows the Guangqiu's MT distance, and the bottom shows the MTN result. So let's focus on one specific example, the heated flow. This MDS plot was created based on the Guangqiu's MT distance. We colored each point based on its distance to the reference point. So here, blue means close, yellow means distant. If MTNN captures the similarity of our Guangqiu's, we should see similar color patterns and also like point arrangements. Here is the MTN plot using the same reference point. The structures and color patterns are indeed similar. And this similarity isn't just limited to the heated flow, but to all datasets. The consistent alignments of clusters confirms that MTN effectively preserves the data's relationships, which is essential for accurate analysis. Let's look at a vortex street example, a pattern similar to hurricanes. Using MTN, we can compare datasets to like in the order of milliseconds versus half an hour with previous methods. This helps us understand phenomena like weather formation more quickly, allowing faster data processing and potentially quicker forecasting during critical times. To conclude, our work transforms multi comparison into a fast and precise running process, enabling real-time analysis and visualization across fields. By advancing topologically aware machine learning, we are not just solving a specific challenge. We are setting the stage for future research that extends far beyond multis. Our approach could potentially reshape how we interact with complex data. I'd like to thank my co-authors and our funding sources for their support, especially our primary funding from DOE OSCAR. I'd also like to give a special thank you to Brian Sumer for his unlimited support from this very beginning, even when I first come up with this crazy idea. Thank you for all your attention. I'm happy to take any questions now.
Thank you so much, Demi, for the fascinating presentation and work. One of the questions I have is, do you have examples pathological examples that show how bad the results can be because these are approximate, or have you not been able to find some examples that your technique that is approximate works, commits errors?
Yeah, that's a really good example. We actually do test out the generalization of this model, speaking we train a data from the other domain outside of the flow data or hurricane data, climate modeling. We use the 3D shape data and then test out the test data from the other domain. And we do find that actually the results still quite good, but I will say the model is not generalized very well with data from different domain.
Okay, but I mean, really great work. There's a question here from Bei Wang. How long is the training time and how many training samples are needed?
Yeah, that's a good question. We do include the training time in our paper. That's actually not quite long. Usually our training size is around thousands of data points, and it takes about 3 to 4 hours for training. And also since our model is generalized in the same domain, so you don't necessarily need to for the same domain data, you don't necessarily need to retrain whenever you get a new data set.
Okay, so thank you so much for your wonderful presentation. Congratulations on your work again. I now am passing on to the full papers chairs, to the OPC.
Thank you.
Okay, thank you very much, Claudio. Please stay in the session. We make it short and you might learn a little bit about your VIS conference in the next few minutes. Next slide, please, Claudio. Claudio, can you take the next slide?
It's there. Oh, sorry.
Yes, I
It
wanted
just
to
takes
show
a while to drop the data.
Yes, that's fine. That's fine. That's fine. Here you can see the 3 overall paper chairs for this year: Niklas Elmqvist, Tamara Manzner, and Holger Teisel. All of them are here, and all of them will say a few words in the next few minutes. Next slide, please. Can you go one more slide, please? One more step.
I'm
There should
already
be more
changed.
on the
Is that
slide.
it changes by it seems to take I'm sorry, like a second and a half after I change. Sorry.
Okay, we see half the slide now, and let me explain half the slide. Then let's see if we get a second half. Here we get a full slide. So the paper chairs committee consists of 3 + 1 + 12 people. The 3 OPCs we already have seen. The 12 area papers chairs. We say something in a few seconds. And something new for this year, we have 1 OPCA. That stands for OPC Oval Papers Chairs Assistant. This is Petra Specht. She was not directly involved in the technical decisions, in the scientific decisions, but she helped us organizing ourselves and smooth the work of the OPC and the APCs a lot. Thanks a lot to Petra. Next slide, please. Talking about the area papers chairs, the APCs. These are actually the guys who did the real work. A lot of work about the whole process of paper selection is in the hand of the area papers chairs, ranging from discussion of borderline papers over requesting additional reviewers to give final recommendations. We, the oval paper chairs, are there for harmonization, calibration, and making sure that the same criteria are applied among the areas, and also for making the final decisions together with the APCs. The APCs did such a wonderful job that I just have to speak out all their name explicitly here. So we had Matt Kay, Adam Pera, Tatjana von Landesberger, Jiahang Zhang, Christoph Gard, Chaoli Wan, Pia Dragovic, Dan Keefe, Ivan Viola, Philipp Sadlo, Steffen Koch, Wen Du. It was a pleasure to work with you guys over the last year. Next slide, please. And in addition, we have these 6 areas. They are given by the area curation committee and frequently updated. And in addition to the OPCs and the APCs, we have the program committee consisting of 142 program committee members. And now you have all the basic knowledge to be able to go through the selection process. And this is given by Niklas. Next slide, please.
Right. So VIS papers go through 2 rounds of reviewing. You can see, of course, first people submit abstracts by the March 21st deadline. And during the time between that submission and the full paper deadline on March 31st, we have bidding and conflicts of interest declaration, and also some moving of papers between the areas to make sure that we don't have too many conflicts of interest among the APCs. And also after the full paper deadline on March 31st, we get rid of all the papers that did not end up being complete submissions. And we also go through, together with the APCs, all the submissions before they get allocated reviewers to make sure that they should not be desk rejected, which could be a paper that's not in scope of the conference, or uses the might be too long, or other reasons. Then we allocate these papers to our PC members together with the APCs, who tweak the assignments. The reviews are sent out, and we want to thank all the reviewers, of course, for helping us with this monumental task this last year. By the review deadline, we then look over all the submissions. We have online meetings with the APCs and in groups, and discuss all of the papers. We identify the ones that are rejected, and that's where our first notification is sent on June 6th. The papers that get accepted in the first round, they're conditionally accepted, get the chance to make revisions over 3 weeks, a little more than 3 weeks. And after they submit a second revision, well, first revision, The PC members are then writing new reviews, and we make final decisions of which papers get rejected or fully accepted to the VIS conference. And then it's just the camera ready. Next slide here. This year, 2024, we had an increase in the number of submissions. Last year, on the right side, you see the 2023 numbers. So we had 43 more abstracts this year, 680 in total, of which 557 full papers resulted. So that's an increase from 539 from last year. 129 were conditionally accepted, which is a decrease. And we heard that earlier, that our acceptance rate this year is actually 22%, whereas it was 25% last year. So the conditionally accepted papers ended up being only 124 being accepted. There were a couple of papers that fell off in the second round review. Next slide. So I encourage everyone to read the preface for the TVCG special issue for the details. And also to keep an eye out for the call for papers for this upcoming VIS 2025 edition, because there will be changes, and we'll talk more about that later. All right, I'm handing over to Tamara. Next slide.
Okay, thanks. And so we have a number of full paper sessions for VIS 24 here in alphabetical order. And I encourage you to attend as many as you can. Remember, with time shifting, you can go back and see more that you missed live stream. You can see even more papers in virtual mode than you could in other modes. So much exciting content for you. Next slide, please. And I want to thank everyone that made this happen. Of course, all the authors, the program committee, the external reviewers, the APCs, the Best Papers Committee, the steering committee, the VEC. Han-Wei, as editor-in-chief of TVCG in particular, is instrumental in this process, along with Daniel Weitzkopf, Shoshielio, and Ross Mayowski. The CS staff, James Stewart from PCS, most definitely Pex Respect. And I want a huge thank you to the general chairs, the web chairs, and the tech chairs who have made this pivot to virtual in an unprecedented 5 days rather than, say, 6 months, which is what it would take in the past. So thank you for letting VIS still continue. There will be a, next slide, please. There will be a town hall where we will talk about some of the things coming up from next year's review process. And that's tomorrow at 3 o'clock Eastern time. So some thoughts about the reviewing process and reflections. Please do accept review requests for TVCG Fast Track Continuity and some proposed changes from VIS 25, and then we'll have some group discussion. So this is part of a larger town hall, but the OPCs will be doing part of that. And with no further ado, I will invite you to experience the rest of the VIS full papers, and thank you very much.
Thank you very much. It was a wonderful session. Thank you.